Good to have you back. I'm glad you decided to come and learn about logistic regression, an important thing in life, to be sure, because what we're trying to do is to basically extend our work from the kinds of regressions that we've been learning about to regressions that describe posterior probability. So basically, if you make a guess about the classifier, so you say you got some data and you classify it as this, and you are given the result that says, no, you got it wrong, it's actually that, and you want to update your belief, you want to update your model. So how do you do it? And so we're in position now to tackle that problem today, and it's called logistic regression. And logistic refers to the function that describes the posterior probability. So posterior probability is typically, something that looks like this. It's a logistic function, and so our problem is, how do we update our model when we have a prediction error? And so that's what we're going to be talking about today. So our posterior probabilities, when you have some class, say class 1, given your data, we knew that, well, this depends on the likelihood model and some prior probabilities divided by the marginal, right? So this is our basic definition. And what we want to do is that we want to model this probability as some, some function, and have some parameters for it and estimate what the values for it are. So that's what we're going to do. So we're going to begin with equal variance in the likelihoods. And so just to remind you, we have some class, we have some other class, and we have our likelihoods, and then we have this other likelihood, and we would like to be able to represent the posteriors using some kind of a model that will have parameters that we can update based on our prediction error. So we're going to begin with the idea that these are normals, so the likelihoods. This is a normal with mean mu1 and variance sigma squared. And similarly, we have another class which has a normal that has a different mean and the same variance. So, of course, what I mean by that is the distribution is defined by the following. For P of x, given that you are class 1. So what's the posterior probability for this? So we have the probability of being class 1 given your x, and that's the prior probability times the likelihood divided by the marginal, which is, in this case, suppose we have two classes. Okay, so that's our marginal. So let's write this now in terms of the exponentials. Let's see what the posterior probability looks like. So suppose that this prior probability is q. So that's q times some terms that depend on the Gaussian, right? And that term is going to have a 2 and a pi and a sigma in front of it here. And that's going to be also in front here. And also it's going to be in front here. So those are going to go away. What I'm going to be left with is just the exponential. Okay, so that's our posterior. All right, All right, so let's divide the top and bottom by the numerator. See what we get. So we get a 1 on top. If you take this, divide the bottom by the numerator, so I get a 1 here, plus 1 minus q divided by q, and I get in the numerator exponential all right. Okay, so let's take these q's inside the exponential. And let's see if we can fit it here. So I get a 1 plus an exponential log of 1 minus q divided by q minus 1 over 2 sigma squared x minus mu 2 squared plus 1 over 2 sigma squared x minus mu 1 squared. Okay, and the point is that if you now look at this, you get a constant term here, some constant, then you get these x squareds that are going to go away because this is a plus x squared, this is a minus x squared here, and so what you're going to get is a linear function in terms of x. So this is equal to 1 over 1 plus the exponential of some constant w0 plus some linear function of x. So in this case, it's going to be some w1 times x. In the case of x being a scalar, if we have vector quantities, then probability of class 1 given x is going to be equal to 1 over 1 plus an exponential of w0, which is a scalar, plus w transpose times x. So this is now a vector. This is a vector. This is a scalar. So a feature space, when it's a vector, the posterior probability is going to be a logistic function that's still a linear function of the input variable x. So that's a nice thing, because what we have is that we have now a posterior probability that can be parameterized in terms of our input x with some unknowns, w0, w, right? So this is the problem of regression, is to finding what those things are. That's how you model your data. You model the data in terms of the probability of it belonging to a class. And we're going to talk about, how do we get these w's. So just to remind you, what we can do is that we can write then, if you have two classes, probability of class 2 given x is just 1 minus the probability of class 1 given x, which is equal to 1 minus this quantity, which is equal to the ratio of these exponentials. And so if I now write the probability of class 1 given x to the probability of class 2 given x, probability of class 1 is this element here, this logistic function. Probability of class 2 is this. So you notice that the numerator here is going to go away with this numerator. I'm going to get 1 over exponential of w0 plus w transpose of x. So the ratio of the posterior probabilities are going to be also linear in the input vector x, and so the log of the posteriors is going to be linear so when this is equal to 0, we have what we call the boundary conditions, decision boundary. Between classes. Okay. All right, so we still don't have a learning rule, so we would like to have a way to estimate these W's. So let's go over the problem statement. So we have some data. And C is my label. So data point X is associated with some class 1, and data point X2 is associated with some class C2. And we have n of these guys. This is our data that we're going to learn from. And our classes belong to, say, 0 and 1. And what we have is that the posterior probability of belonging to class 1 given some data, we wrote as a logistic function. I'm going to put a minus here, WXI. And so that's Q. The logistic function's posterior probability, we're going to label it as Q, and we know the shape of this function. So we have some data that we've been given, and it has some x's in it, and that is going to look like this: 1, x1 of I, x2 of I, so some vector, x say d of I, and then W is W0, W1, WD. So that's what I mean when I write W transpose times Xi. Xi is a vector. I'm going to add a 1 to it. So then that takes care of W0, and then the rest of W's are there. All right. So then the probability of being at class 0 given Xi is 1 minus Qi. So now what I want to do is do maximum likelihood to find W's, the model parameters. So we have some posterior probabilities that we can write in terms of our W. Here it is. And we have some data, and we want to write the likelihood of this data given the parameter W that we're trying to estimate. Once we write the likelihood, then we maximize the likelihood to find our W, and that's going to be our learning rule. How to update your parameter W in logistic regression based on measurements that you've made. All right, so let's write it. So we need to know the probability distribution of the class given that, we got some data Xi. And so here it is. You can only have two numbers, class 1 and class 0. And here it is 1 minus Qi if it is class 0, and Qi if it is class 1. So to write the probability distribution for this binomial system, what we have is that we have Qi raised to the power of Ci times 1 minus Qi raised to the power of 1 minus ci. So whatever is the class, it's what the power. So this describes basically the distribution, the probability distribution for these two probabilities that we have. So why is this useful? Because we need to write the likelihood. So we need to know the likelihood of our function, which had, class in the first data point, the second data point, the nth data point. That's the data that we were given that we had these inputs, x1, xn, and we had some parameter w that we're trying to estimate. So this is just a multiplication of these guys. So what we want to do is that we want to find a w that maximizes this likelihood, where q's are the posterior probabilities of belonging to the class 1. So we take the log of this, and then we find the derivative of the log with respect to the w that we're after. So log of this probability is going to be the sum of this. Okay, so that's our log likelihood in terms of the posteriors, Q, and the class CIs. This is our data. Now what we want to know is that, how do we maximize this likelihood in terms of the parameter W? So what we need to do is that we need to find the derivative of this log with respect to W, where Q of I is the posterior probability. Okay, so I'm going to have to do a little bit of math. So let's see what we can do with this. So what that function is that we have 1 plus the exponential of minus W transpose xi. That's equal to 1 over Q of I. So therefore, exponential of minus W transpose xi is 1 over Q of I minus 1. And this is useful because this exponential allows us to now take the exponential and take the log of both sides of this, and so we get minus W transpose xi is going to be equal to the log of the right side, which is log of 1 over Q of I minus 1. So, which is equal to the log of Qi 1 minus Qi. Okay, so to find this derivative of this log with respect to W, I'm going to do the chain rule. I'm going to try to simplify things a little bit. What I'm going to say is that I'm going to find first the derivative of the log with respect to Q, then derivative of Q with respect to the W that you're interested in. So to show you that, let's keep on working on this function here. So what I can write then is that W transpose xi is minus the log of 1 minus Qi divided by Qi. Okay, so what's the derivative of W transpose xi with respect to Qi? Well, this derivative of this guy with respect to Qi, which is going to be the inside of the log, which is going to be minus qi, 1 minus qi, times the derivative of the inside with respect to qi, which is going to be minus 1 over qi squared, which is going to be equal to 1 over qi 1 minus qi. So derivative of w transpose xi with respect to qi is this, and so it can be shown that derivative of qi with respect to w transpose xi is the inverse of this. From this, I have this. So let's get back to our likelihood now. So how do we use this information to find our derivative? So we had log of the probability of these classes given x and w, that was equal to the sum of ci log of qi plus 1 minus ci log of 1 minus qi. So what I'm going to do is I'm going to say derivative of this log with respect to w is equal to this, but what I'm going to do is to find the derivatives using the chain rule. So that's equal to the sum of the derivative of this log with respect to qi times the derivative of qi with respect to dwt xi times derivative of dw xi with respect to w. So I have this done over here. I can find derivative of my log likelihood with respect to q, and I can certainly find derivative of w transpose xi with respect to w. So let's see. So this is I is equal to 1 to the number of data points n. So this, the first term, derivative of the log with respect to qi, this derivative of this guy with respect to qi. So that's ci over qi minus, the derivative here is going to have a negative on it, 1 minus ci, 1 minus qi. That's the first term. The second term here is this. The third term is this derivative, derivative of w transpose xi with respect to w, which is just, of course, xi. All right, the first and second, these two things, when I multiply each other, they're going to simplify. That's equal to the sum of qi 1 minus qi which is equal to the sum. Look, this cancels with this. The numerator here is just going to have ci minus qi left in it. So it's going to be something rather beautiful. The class minus my posterior probability guess of the class times the input xi. This is your prediction error. So we have the gradient of the likelihood with respect to the vector w that we were after. So xi is a vector, right? That's the feature space. So the derivative of the likelihood with respect to the vector w is the sum of the errors over all the data points times the inputs over all data points. So what this tells us is that, you know, a reasonable learning rule might be something like this. W of n plus 1 is W of n plus some learning constant times your prediction error times the input on that trial, where this Q is the logistic function that relates to input x, multiplies it by the weight w, and gives you the posterior probability. So the nice thing that we got was this. Derivative of our likelihood with respect to the weight is this sum of errors. It's like a batch learning error. And so this is like an approximation of it, of this batch learning rule. So we can take another step and get a little closer to a better solution, and that we can do using Newton-Raphson. So if you remember, in Newton-Raphson, what we need is not just the first derivative of the likelihood with respect to w, but we also need the second derivative of our likelihood with respect to w. And so that's what I need to find. So just to remind us where we are. So we found that the first derivative of our likelihood with respect to this vector w that we're trying to find is the sum of all the labels minus all the posterior probabilities that we guessed times the input, xi, on that trial. So let's write this in a matrix form. So let's say that the vector q is the q on the first trial, the q on the second trial, the posterior probability, our guess, and this is the nth trial. And then we have this vector c, that was our labeled data on the first data point, the second data point, the nth data point. And then the matrix x, we're going to write it as the vector x on the first data point transpose on the nth data point transpose. And so if you have that, then we can write this sum, the derivative of our likelihood with respect to the weight that we're after, as x transpose c minus q, which is the prediction error vector over all the data. So that's useful because that tells us the first derivative. We need the second derivative now to form our Newton-Raphson technique. So we need to know what's the second derivative of our likelihood with respect to the weight that we're after. So, well, here's our first derivative. So we have to take the derivative of this with respect to w. So there's going to be a sum. And what I'm going to do is again use the chain rule. I'm going to first take the derivative of this with respect to q, then take the derivative of q with respect to w transpose x, then the derivative of w transpose x with respect to w. So that's the sum of the derivative of this function with respect to qi, then the derivative of qi with respect to w transpose xi, then the derivative of W transpose Xi with respect to W transpose. That'll give us the second derivative. Okay, so this isn't hard to do. I'm going to get a sum. The first term, well, there's only one Q here that's multiplying by Xi, so I'm going to get minus Xi. The second one I've already done. That's Qi, 1 minus Qi. The third one is just X transpose. So I have now the second derivative. Let's write this in a matrix form. Let's just write this sum as a matrix form. So let me define a matrix Q. That's going to look like this. Q1 times 1 minus Q1. Posterior on the first data point times 1 minus that. Q2, 1 minus Q2 until the last data point. Those are the diagonal elements. So what that means is that the second derivative is minus X transpose QX. Okay. All right, let's put the story together now. So we had the posterior probability of it being to some class I, given the X data point, was a logistic function, 1 plus an exponential minus W transpose Xi. We had the first derivative of our likelihood with respect to W. We call this Q. The first derivative of our likelihood with respect to W was X transpose C minus Q. We have the second derivative, which we've written here. So given that we have the second derivative, now we have our learning rule that says your W should be updated based on X transpose Q X minus 1, the inverse of the second derivative times the first derivative, C minus Q. So this is called iterative reweighted least squares, which what it's doing is to give you regression using batch learning on the parameters of the logistic function. All right, but I want to give you an intuition about what it's doing. So this first term here, X transpose C minus Q, this is just your prediction error, right? This is just a normal way of learning. But what is this doing? Let's see what this means. So Q, it's got these elements in it. Q times 1 minus Q. So what's Q times 1 minus Q? What does this mean? Because we're going to invert it here. So let's plot this function. So Q is of my posterior belief. So at 0.5, I have the least certainty about the classification. So if I plot 1 over Q times 1 minus Q, I'm plotting this guy here, Q inverse. And here's what it's going to look like. So if Q is 0.5, this function, 1 over Q1 minus Q, is going to have the smallest value. As Q gets smaller, this rises. As Q gets bigger, this rises. So at 0.9, it's going to be high. At 0.1, it's going to be high. So what it's doing is that it is weighting the error in your prediction. What it's doing is to saying that if you made a prediction error, what you should do is to weigh it by this quantity, which relates to how certain you were when you made that prediction. This is Q. On the x-axis, we have Q. So when Q is large, you were pretty certain, yet you were wrong. You should learn a lot. When Q was 0.5, you were very uncertain, right? Because that's chance. There, the learning isn't very high. And then it becomes high again on the other side. So this is basically weighing errors. Based on the uncertainty of the prediction. Okay, iteratively reweighted least squares. All right, so we did all this for what? For a specific class of problems when the variance of our likelihoods was equal. So that's a pretty special class, right? Not very likely you're going to find that in real data very often. So how do we fix the problem so that we can generalize to a more realistic scenario? What you're going to see is that the important idea was that we were able to write the logistic function in terms of linear function of the x variable, the input, right? So if you have non-equal variances between your data, then what you do is that you're going to see that your result is going to become a quadratic function of x, right? It's not going to be that different from what we had before. But instead of modeling it as a quadratic function of x, what we do is that we still model it as a linear function of a nonlinear function of x. So the results are going to remain the same. We're still going to have some weighting of x, but x won't be linear anymore. It's going to be a nonlinear function of it. There we're going to have a basis function. And that basis function is going to be a vector. It's going to say, we have x squared, we have some other, versions of x, and all of them are going to have weights. And so the result that we got with iteratively reweighted least squares is still going to hold even if we have non-equal variances. I'll show you that. Okay, so unequal variances. In the classification problem. All right, so we have our posterior of belonging to class 1 given x. That's our prior times our likelihood divided by the probability of x, which is just probability of c is equal to 1, given the probability of x, c is equal to 1, plus the probability of c is equal to 2, given the probability of x, given c is equal to 2. So now we have Gaussians with unequal variance. So this is equal to All right, so this is our posterior. As before, we divide the numerator and the denominator by the numerator. So I get a 1. I get a 1 plus this term All right, we take the ratios on the outside of the exponential, put it inside, and simplify our ratio. I get a 1 plus an exponential, a log of 1 minus q sigma 1 q sigma 2 minus 1 over 2 sigma 2 squared x minus mu 2 squared plus 1 over 2 sigma 1 squared x minus mu 1 squared. Okay, so you see now we have a quadratic function of x. This x are not going to go away. They're not going to cancel each other. And what this is equal to is 1 over 1 plus an exponential of some w0 plus w1x plus w2x squared. So the posterior probability is going to have a quadratic function of x in the exponential. All right, so what this means that I can write the posterior probability of some class I given xi as 1 over 1 plus an exponential of some w vector transpose some g vector of xi. And let me show you what I mean by that. So let's define g of xi, our basis function, to look like this. 1, x1 of I, x2 of I, x1 of I, x2 of I, x1 squared of I, x2 squared of I. So that's what I mean by my basis vector. And so if I now define the matrix X as G of X of I transpose G of X of N transpose, if that's my matrix X, then my learning rule for this is W of N plus 1 is W of N plus X transpose Q X minus 1 X transpose C minus Q. So what I did is that, let's go over what we did. We found that the posterior probability is going to have nonlinear terms in the logistic function. So we defined a basis set that has those nonlinearities in it. We write our logistic function in terms of a linear function of W and a nonlinear function of X, so then the result that we had before still holds. Okay. So in principle, regardless of whether the variances are equal or not, your logistic function, as long as it's normally distributed, can be written as a linear function in the parameters that you're trying to find, W, inside the exponential, which means you can apply iteratively reweighted least squares and find the parameter W that maximizes the likelihood of the data that you have. All right, the final thing I want to tell you is about what if you have multiple classes. So far we've been just more or less just looking at 2 classes, but let me now briefly tell you what the problem becomes when you have K classes. So in the case of having K classes, then what you want to do is to model the ratio of the posteriors with respect to one particular class. So say class K, last class. So you have k classes, and let's pick one of them as the one that we care about, and we're going to model everything with respect to that class. So what we care about is the log of the probability of, say, class 1 given x with respect to this special one, class k. So we just saw that this log is going to have a linear function. So it's going to be a W transpose of, say, 1 comma k times x. So it's going to be a linear function of the input vector x. And let me call this M1, which is basically saying that the ratio of the posterior probabilities, I'm going to have some number, something, I'm going to call it M1, which is the ratio between class 1 to class k. So I want to show you the derivation that tells us how do we compute for any particular class its posterior probability if you have k classes. And the idea is it's going to use something called a softmax function, and I'll show you what that means. So to proceed, we want to know what's the probability of C being some class I given x with respect to the probability of it being class k given x. And so that's equal to, I have the log of that is equal to m1, so this is just exponential of m sub I from this definition. So what this means is that the probability of the class being I given x is the exponential of the ratio of the log of the posterior probabilities times the probability of it being class k given x, just from this equation, just writing that out. So the other thing that we need to know is that, well, the sum of all of my posterior probabilities have to be equal to 1. So I have k classes, and I have the probability of each one of them given x. The sum of that has to be equal to 1. So what this means is that the sum of I is equal to 1 to k minus 1 of this, which is the exponential of mi times probability of C is equal to k given x, right? This equation here, I'm just writing it down here. So this is from I to k minus 1 plus the probability of it being class k given x, that's equal to 1. And so let's factor out probability of it being class k. That's equal to 1. So then the probability of it being class k given x is 1 over this quantity. So now I have this representation, and I want to now use this in this equation. So look, probability of it being class I is an exponential times probability of it being class k. So that means probability of it being class I given x is this times exponential of mi. Exponential of mi divided by the sum of all the other classes. I'll call this J. So if I have k classes, I can write the probability of any particular class in terms of what's called a softmax function, which is the ratio of the posterior probability for that class to the sum of all the other classes. And what's important here is that mi is a linear function of x. And so I have found a way to write the posterior probability of a class when I have k classes in terms of x, and they're all going to have linear components in them. Okay, so this brings us to the end of how to use regression to do classification. So instead of, saying that let's have the output being class as a linear function of x, what we did is to say, let's form posterior probabilities. Let's then model the posterior probabilities in terms of the parameters of our model, w, and the input x. And so this way, we form a model that says when you're given a data point, how likely it is to belong to a particular class. So you can say with 80% probability it belongs to this class. And so whichever has the highest probability wins. So this is very different than thinking about using regression to classify your data, which would say basically it belongs to this class. This is saying I can tell you with this probability it belongs to this class. Okay. So next week, Ketch and Zhang is going to talk about support vector machines, which is a way to find basically that basis set. What is the optimum basis set to use to transform your input space, x, so you can represent the output that you want? And then the week after, you're going to hear from Renee Vidal, which is going to talk about dimensionality reductions. You have many dimensions in your input, x, and you want to know what's the relevant one that I should consider when I build my models. Is there a way to reduce that space to something smaller so I can model in that space rather than in the gigantic space? And that will be principal component analysis. So a way to reduce the dimensionality of your data set to something that has most amount of information in it in some compact form. Okay? And then when we're done with that, we'll now, after that, go over unlabeled data. So you've been given some data, but you don't know, what belongs to what. You want to classify it based on the statistics of the data itself. And that'll be the beginning of thinking about unlabeled data classification. Okay. Glad you were here. Hope you have a good weekend. I'll see you Tuesday.